Alright, we are dividing radicals here. So we're going to take a look at a couple different things. Maybe a simplified form of a radical. And we're going to kind of take a look at that. We're going to talk about the division property of radicals. And then rationalizing with one term and rationalizing with two terms. But essentially, we're going to take a look at simplifying radicals. And it's kind of the same idea of radicals as multiplication of radicals. In other words, if we had, or of simplifying simplifying radicals like square root of a to the third power, well, that's not simplified because third is bigger than 2, so essentially we've got to kind of rewrite that as square root of a squared times a to the first, and that becomes a times square root of a. So something like that. But essentially we're going to, step number 1 is going to be the most important one. Make sure there's no factor in the radicand inside the square root. That is a power that's greater than or equal to the index. This guy greater than the index, so we've got to simplify him out by separating and conquering. This guy is still equal to the index, so we've got to simplify him to get a, and then that square root of a stays inside the house. So that's kind of what we're doing there. And really, that's the whole idea of simplifying a radical. Step number 2 and 3 are what we're going to talk about here, simplifying fractions or simplifying numerators and denominators. Make sure there's no radicals in the denominator, and make sure that the radicand has no fractions. So we're going to really kind of take a look at these two rules, 2 and 3, called rationalizing the denominator. So we'll take a look at some of those here. So essentially this division, first step to divide and simplify division of radicals is to kind of understand that we can separate and conquer, just like we did with multiplication. Square root of a times b is equal to square root of a times square root of b. Square root of a over b is square root of a over square root of b. We can separate and conquer, just like we did with multiplication. Because square root of 4 ninths, well, we can separate that and to say that this is the square root of 4 over square root of 9. The square root with the index has to stay the same. When we separate these out, the index has to stay the same. But square root of 4 is easy to work with. Square root of 9 is easy to work with. Here's a 2, here's a 3, done. And that's what we're trying to do, is just kind of separate and conquer. So let's take a look at using that idea here. First thought would be, can we simplify this fraction in here? A to the 10th over b to the 4th. Well, the bases are different, so we can't simplify, but we can't simplify it as a fraction. But we can separate as far as radicals and conquer. Alright, so this one would be square root of a to the 10th over square root of b to the 4th. And now we just separate and conquer. I've got square root of a to the 10th gives me, well, let's see, a to the 10th. If we're taking a square root of it, I'm going to say it's a to the 5th squared, square root of it. Square root of a perfect square means the base comes outside the house. This becomes a to the 5th power. This becomes b squared. B to the 4th power square root is b squared squared, square root, b squared comes outside the house, just like this. Alright, how about number b? Can we simplify the fraction? 20 and 9 don't simplify, so, alright, well, see if I can move this over, give us a little bit more space. Oops. Alright, apparently not. This becomes square root 20x cubed over square root 9. Alright, sounds easy enough. Or easier, that's our first step, is separate and conquer. Square root 20, square root x cubed over square root 9, 3. Square root 20 is square root 4, square root 5. Square root x cubed is square root x squared, square root x, all over the same denominator, 3. Alright, square root 4 is 2, square root 5, square root 5, square root x squared, square root of a perfect square, the base comes outside the house as x, square root of x stays as square root x, all over 3. Oops, sorry. Make it pretty. Combine things that are outside the house, 2x. Combine things inside the house, square root 5x over 3. Simplify if we can. 2 and 3 don't cancel. Factor out, simplify. So there's our answer, 2x square root of 5x over 3. It is simplified because all the radicals are simplified. There's no fraction inside the radical. There's no nothing inside the radical that can be simplified. In other words, x to the first power is smaller than this index of 2, so therefore the x stays inside the house. Done. All right, a couple more examples, I suppose. Let's see. A and 1 again are going to be similar. B and 2 are going to be similar. So let's take a look at A and 1. We'll take a look at A and 1. Let's see. Can we simplify our fraction inside the house? No. All right, well, let's separate and conquer. C to the 4th power over square root 49. C to the 4th power. C to the 4th power. If we're taking the square root, we can rewrite it as C squared squared. We're taking the square root of it. Square root of a perfect square means the base comes outside the house. Base comes outside the house as c squared. Square root of 49, 7. Done. This guy as well, same thing. 12 b to the 5th power over 25. Can't simplify the fractions, so we separate and conquer. Square root 12 b to the 5th power over square root 25 equals square root 12 square root b to the 5th power over square root of 25, 5. This becomes square root 4, square root 3, square root b to the 4th power, square root b to the 1st power over 5 becomes 2 square root 3 square root b, or sorry, not square root anymore, because the square root of b to the 4th power is b squared, square root b over 5. Combine everything that's outside the house. I got 2b squared square root 3b in my numerator over denominator 5, and I'm done. 2 and 5 outside the house don't cancel. There's no common factor, so we're done. And we've simplified. There's no fractions inside the radical. The index b to the 1st power is smaller than the index of 2 where I'm pointing, and we're done.